All right, so in this video, we're going to be looking at logistic regression models, which we're also going to get from the general linear model function that we saw in the previous video. And we're going to be looking at some diagnostics for our logistic regression, our classification task as well. So we're going to start by loading our data set. We're going to use the MT-CARS data set. And we've seen the MT-CARS data set in previous videos, but we'll go ahead and look at it again. And we can see we have some 0-1 variables that we can use those to predict in logistic regression models. That's what logistic regression wants. It wants a 0-1 variable, yes or no, success or failure. And we can use any of the other numerical variables in order to do that prediction. So we're going to start by creating a GLM model, and we're going to specify the formula. We're going to predict the AM variable, which is the automatic versus manual transmission, and we're going to start by trying to predict it using horsepower as our variable. No particular reason. And to specify the logistic regression, we're essentially going to specify here that it's a binomial family. So that's that 0-1 prediction, as opposed to, again, success or failure, as opposed to a sort of linear model where we don't actually want a general linear model in the sort of ordinary least squares type. We want this logistic regression model, and this is how we get that. And so then we're going to run that, and then we're going to look at the summary. And so it does output coefficients, but remember that logistic regression is using a log odds model in order that we're actually modeling with a linear equation. And so this would be the linear equation that goes in our exponential function in our logistic function after we solve it for our probabilities. So we could say, for instance, the horsepower variable is going to slightly decrease the log odds of our result. Now, the p-values here are not very high. In fact, they're not high at all. This suggests that our horsepower variable is actually not very good at doing this prediction. And so maybe we should choose a different variable in order to do our modeling with. So I am going to try a different variable. Let's try the cylinder variable and see how well that does. So if we run that. Okay, great. Now we have statistically significant coefficients in our model. And we can see that, for instance, if we want to compare models, the AIC here is 45. And in this case, the AIC is 37. The fact that the AIC went down between models on the same variable, that tells us that the second model is an improvement over the first model. For logistic regression, you can also look at the change in the residual deviance over the null deviance. So for instance, here the null deviance is 43 and the residual deviance is 41. Those are very similar. That means that our horsepower variable is not doing a very good job predicting the outcomes different from what it would be if there was no variable in the model. But when we actually use the cylinder variable, we see a drop from 43 to 33. So that is a significant decrease in our residual deviance, and therefore over the null deviance, and therefore that is, again, an indication that this is a better model than we had before. Now we can go ahead and we can plot our model on a graph. So I'm going to pull in ggplot. And we do have to be have some extra functions in ggplot in order for the stat smooth function to actually create our logistic model on the graph rather than using some of its other built-in functions. So first we're going to put a layer for the point plots, and then we're going to add, you can use, in principle, you can use geom smooth or stat smooth. They're mostly interchangeable, but in this case, I'm using stat smooth. There are some slight differences between them. And so generally speaking, if one doesn't work, use the other one. Method.args equals list family equals binomial. So because we're not using just the linear one, we have to specify that in the general linear model, we have this argument for the method where we're specifying that it is not a Gaussian model, it's not a standard linear regression model, we're doing a logistic regression model. And so we have to specify this argument for the method as to be in the binomial family. And so if we run that, we can see this curved line is going to be our logistic regression model. Now, we see all the points are actually plotted on top of each other because there's actually only 3 levels of the variable. And so we can't actually see like how many different outcomes are plotted in each of the categories because they're plotted literally on top of each other. If we were to change this to another variable, like say the HP, the horsepower is a more continuous variable, and you would see things spread out a little bit more, but the model is weaker, and so it's not as good as this model. This model does a little bit better job of predicting. There are categories in each of there are vehicles in each of these 6 categories, automatic or manual, and however many cylinders. It's just that there are certain numbers of them in each of these categories, and there's more over here and fewer over here, and so therefore you get this probability model. So you do see some differences. There's a lot more variability and uncertainty in this one, even though the graph looks a little bit easier to interpret because things are not plotting literally on top of each other. So when you're dealing with these discrete categorical variables, you do have to be a little bit careful. We could try one more, maybe MPG. See how MPG does. That actually does a little bit better. This is sort of more like what you would expect with logistic regression models. You would see this sharp curve in the middle, and you can see that at least up here, the category 1 in the automatic versus manual category, the MPG, the higher it is, the more likely it is to be in category 1, and the lower the MPG is, the more likely it is to be in category 0. Now, we don't have to only use one variable at a time. We can use multiple variables in our logistic regression model. We won't be able to plot them because we have only 2 dimensions to plot. And so if we use 2 variables and a third one as our model, we were not going to be able to create a graph of them, but we can create the linear model. So here I'm going to create a model using MPG. We can see from the graph that that actually is going to do a bit better. And I'm going to use one other variable from our data set. And then we're going to summarize it. And so, again, all of these coefficients, the intercept, the MPG, and this carb variable are statistically significant. And we can see that in both of these cases, the coefficients of our variables in our model are positive. That indicates that the log odds are improved by having higher values for MPG or carb. And as we've seen, we can also plot the diagnostics. So down here on our console, again, this is the residual versus the fitted values. Ideally, a residual plot should be plotted against the um, the x variables or the original y variable, but this is one of the analysis plots that's available to us. The normal probability plot, we can see there's a lot of variables that don't make this look terribly normally distributed, which could be a flaw in our assumptions, our scale location, and our residual leverage. Maybe we shouldn't be having a linear model at all. So there are some other things that we can look at in addition to the possibility of having other variables in the model. There may be some nonlinearity going on, for instance. Now, when we want to test the value of our model, there's a bunch of different diagnostics that we can perform. So we're going to load another library. Again, if you've never used this library before, make sure that you install it under Tools before you try to load it here. And then we're going to take the predicted values and we're going to round the predictions. Now, typically, the cutoff value for the predictions, they come out as probabilities, and then the cutoff values for the predictions is going to be, if you just round it at 50%, the ones above 50% will round up, the ones below it will round down, and you'll get your 0, 1 outcomes. If you need to round them at a different point or, convert like at 0.6 or something, then you don't want to use the round function in order to do that. Now here I'm just converting my automatic versus manual into a factor variable so that I can create a confusion matrix. So my original variable versus my predicted outcomes. MT cars, I had an extra thing. Try again. Because I didn't spell predicted correctly. There we go. Now, if we scroll back up, all right, so I was I was a little confused because I got a weird outcome from that result that I was not expecting. And it turns out that when you actually run this predict function here, and I'll just run it on the screen so we can see it, what the outcome is. It's actually, our model is not quite doing what I expected it to do because it's predicting values that are like all the way up to -5 and down to +5, almost 6 in this case. And so when I was generating the rounding in the previous example, it was rounding up to an integer and then not giving me a 0, 1 variable at all. It was giving me a discrete variable between 1 and between -5 and 6 or something like that. And so I was getting this crazy confusion matrix. And in order to actually try to compare them, it was actually forcing the original data into a similar range of values, and it was just a mess. So in order to account for this, what I've assumed for our simplified version here is instead of rounding, I'm using an if-else statement. And essentially, if you're above a 0.5 probability, you're going to round up to 1. And if you're below a 0.5, you're going to round down to 0. And that will give us our 0, 1 outcomes that we expected. And then, so that's using an if-else statement. You can use this kind of a thing if you want to change that result from 0, from 0.5. It's the common rounding threshold. You can also use this as a default. Now, I'm not sure why a logistic regression model with a binomial family is giving us outcomes like this. So there's something weird happening in this particular analysis. And I went back and I put the family in the binomial, and I'm still getting those same weird outcomes. But when you do this, when you use the if-else statement, we can run these, and then the confusion matrix actually makes a lot more sense. If we look at the confusion matrix we get from this if-else construction, then our references were originally 0, 1, and our predictions are also in the range of 0, 1. And we see that 18 of the original variables that were actually 0 are predicted to be 0, and only one of them that should have been classified as a 1 is actually modeled as a 0. And of the variables that were originally a 1, 10 of them were correctly identified as a 1, and 3 of them were misclassified as a 0. So when it was producing these like 12 crazy categories from -5 to 6 or whatever it was, we were getting only a 12% accuracy. So something was clearly amiss. Here, by just using this if-else condition, above 50%, give it a 1, below 50%, give it a 0, we're getting 87.5% accuracy, which is much more like what you would expect. So again, I was getting a slightly different response than I was expecting, but if your problems are actually within that 0, 1 range, the example with the rounding will work just fine. But if not, then an if-else statement will be sufficient to handle this. And you get a confidence interval for your accuracy. And we get a whole bunch of other statistics that are pre-calculated for us. So for instance, sensitivity, specificity, and various other categories that we can look at separately that have to do with the ratio of correctly predicted things versus incorrectly predicted things in various different ways. Now, we can also look at some additional diagnostics that have to do with our ROC curves. And so we're going to, again, load another package called ROCR. Again, load it, install it from the tools menu before you try to run it. And from this, we're going to calculate some predictions That's because there's no s on the function. And because there's no s on that one either. And if we calculate the performance and the type is accuracy in this case, and then we can plot it. And we can see where the cutoff value has the highest performance. We can see that if you cut things off here, you get slightly higher performances. Again, the range of our outcome is a little weird, our response variable, but you can see where you should set the predictions in order to get your highest response rate. It does look like the most accuracy is actually obtained here right below 2. So that's something that we could experiment with our if-else statement to see if we can adjust this spot where we do our break between the 0 and the 1, if we can get our accuracy improved ever so slightly. Now, we can also do some additional graphs. So, for instance, we can, instead of doing accuracy, we can do cost. We can plot the error. And we should change the name of these. We can also plot the TPR. And we'll plot each one of these in a second. And we can also plot sensitivity and specificity. And then we can plot each one of these. Where is the error the lowest? Again, it looks like it's here around like maybe 1.5 or something like that. The TPR is the true positive rate. And then, oops, our last one get sensitivity versus specificity. We can use the graph to estimate the optimal cutoff values, or we can actually have that be done by R. So let's look for our max indicator. And I'm going to make sure that I didn't mess it up by running something weird earlier. Oops. And so we can get the accuracy up to 0.9 if we specify the cutoff to be around 1.4. So let's see if we can actually do that. Let's go back to our confusion matrix. And we're going to change this cutoff value to 1.4. And then we're going to run that. And indeed, we get more things correctly classified as 0. We haven't changed the correct classification as category 1, but we do get at least one more thing pushed over into the correctly predicted category. So that makes our probability go up. So we were able to, by using this analysis, we were able to find that cutoff value that will optimize our predictions based on our model. And then the last thing we want to do is actually calculate the ROC curve. So the ROC curve is based on a relationship between the true positive rate and the false positive rate. And so if we plot that, LWD equals 2. This is our ROC curve. And we can calculate the so basically the sort of random chance line would be this straight line. And so anytime that you're above that straight line, you're outperforming random chance. And then from there, we can calculate the AUC, which is the area under the curve. And that is a measure of how good our model is. The closer, the higher it is, the better, generally speaking, closer to 1. And we get 95%. 95 is the area under the curve. So relative to 1, this is very good.